This is problem 11-7. It's on page 450 of chapter 11. Specify a key for both the sprocket and the worm gear from example problem 12-3. Note the specifications for the final shaft diameters at the end of the problem. So we have to go back into the example problem. This is not problem number 3 that we just worked. This is the example problem in the text. And extract some data. So let's see. Oh, no, it's actually chapter 12, excuse me. So future chapter. So let's see. Design example 12.2. Let's go to 12.3. If I can find it. Here we go. Page 472 and 473 looks like it continues on. Okay, so what are we doing? We are designing a key. So we're going to design a pin and a key for both the sprocket and the worm gear from the problem. Okay. So let's see, the sprocket and the worm gear, where are they? Well, there's a chain sprocket at B, and there's a worm gear at D. And so what we'd like to know is the torques at those points. Now it looks like there's just those two machine elements besides the bearing, so I assume that the torque at both ends is the same. Let's see if they say here. There should be a torque diagram here somewhere. There's the summary of the shaft diameter, so we can use that. In fact, let's go ahead and write it down. For the sprocket, looks like the diameter D2 is specified as 2 1/4 inches, and for the gear, which is a worm gear, the diameter is specified there, and they called this D2, by the way. So at the worm gear, that's D5, and it looks like they specified 1.5 inches there. Now let's verify that the torque is the same throughout, and I haven't missed anything. Let's see.
The torque diagram of 472.
Where is it? 472?
Red on the page.
Ah, thank you. Yeah, so it's sprocket B and sprocket D. Looks like the torque comes in on sprocket D and power flows out of sprocket B. So they're the same. So there's our torque. So the torque at both places is 4,168 inch-pounds force of torque. I prefer to use pounds force inches for energy rather than inch-pounds force. I don't know what I've done with these problems. Oh well, anyway, I'll just solve it at the board. So we're supposed to specify a key, so what we'll have to do for both of these is specify a key, let me just call it height. This is going to be the same as the width. So we'll go back to the same table. Oh, do we need speed? I don't think we need speed, we just need torque and diameter. Okay, let's go back to the same table where they've got the standard key sizes and specify a key here. So page 425 again. If the diameter is 2 1/4, let's see, then 2 and including, looks like this is going to get a 1/2 inch key. And the 1.5 inch section, let's see, that's between 1 3/8 and 1 3/4, so that's going to get a 3/8 key. And so now we'll just play the same game. Now here I'm assuming that the key is the weak link and the shaft and the hub are stronger. And so I gave you this problem on purpose so that you would get to use equation 11.5 on page 429. So L min equals 4Tn divided by D divided by W divided by the yield strength. Now notice that they're calling for, this equation calls for the tensile strength, right? The tensile yield, yeah.
So are we going to use the key instead of the pen?
We're going to do both.
We're going to do both?
Yes, we're going to use a key first and then we'll use a pen next. The pen will be about like the other one, so it won't be much difference. Okay, so we have to decide what we're going to use. We used 1018 last time, and I don't think we were constrained this time, were we? 7. No, we are. It says use 1018 unless a satisfactory design can be achieved. Okay. Did they give us a hub length? I don't think he gave us a hub length in the example problem. Yeah, that comment applies to problem 7. Let's see. Because in the shaft design example problem, you're not really interested in the length beneath the elements. You're interested in the loads at the element points. And so your author doesn't have any information about the width of any of these elements. Okay, so we don't have any restrictions that we know of. Of course, if we figure out that we need a 10-inch key, obviously that's not going to work, right? We need a 5-inch key. That's probably impractical as well. So let's see. I guess we're supposed to use 1018. It seems a little boring because that's what we had before, but we'll use it. Anyway, the yield strength for 1018, we just found out the last problem was 54 KSI. And so we'll use the same thing again. We'll use the yield strength again to figure this out. So let's see. What do we got? The torque is 4,168 inch-pounds force. The safety factor, I'm going to use a safety factor of 3 again. The diameter, well, let's see. If we're sizing it for the sprocket, then that would be 2 1/4 inches. The width is the same as the height because we're talking about a square key, so 1/2 inch. And then the yield strength, 45, try to do it again. 54,000 pounds force per square inch. Okay, so again, the square inches go away, pounds force go away, and we'll just have inches. So please plug this into your calculator. And then we'll have our minimum key length. How much? 0.823, thank you. And then for the gear, the equation is going to be exactly the same because it has the same torque transmitted, same safety factor. The diameter of the shaft is different. The diameter of the shaft is 1.5 inches. And the key dimension is 3/8. Now what that's going to do is that's going to bump up the length of the key required. Okay. So if you wanted, if you still have this number in your calculator, you could multiply that number by 2.25, then by 1/2, and then divide by 1.5 and divide by 0.375. Okay, and that would give you the minimum length under the gear. Or you could just plug all these into your calculator. It's up to you. Anyone have a number for us? $1.65. Anyone second that?
Yep.
Okay. So what would I do? Well, I'd probably take this one to 1 inch. And I'd take this one to 1 3/4 inches. What would happen if that was too long? What if the hub was not 1 3/4? What if all I had was 1.5 inches? Then what would I have to do? Stronger material. I couldn't use 1018 anymore, right? I have to choose something that has a bigger number here, so this denominator would increase, which would decrease the required length of key. I would not want to go up to the strength of the shaft or the hub, though. Does that make sense? I would want to go below that so that the key would be the first thing to fail. Okay? So that was pretty straightforward. Now let's design, yeah. Okay. Now let's design a pin connection as well. We may as well. It won't take us very long. And let's see, pin connections. They were there just a moment ago. I can't find it. 434. 434, thanks. Okay, so equation 1119. Would have the diameter of pin required is square root for T over D pi design stress. Okay. All right, so what I'm going to do is assume that I want a pin that will shear. So I'm just going to use the yield strength over 2. In other words, the shear yield strength. Okay. Assuming we have 1018 again, this would be 4 times 4,168 inch-pounds of force divided by the diameter. Well, for the sprocket, that's 2 1/4 inches. And we need pi in it. Then we need the yield strength over 2, which was 54 KSI over 2, 27,000 pounds force per square inch, and then square root. That takes care of the pounds force. Yeah, the inches will cancel, we'll end up with inches again. How much?
0.3.
0.3? Anyone second that? Got it? Okay. So what would I do here? Well, I'd use a 3/8 inch pin. That's what I would do. Because it's 0.375. That way it'll shear at a little higher load. Anyone want to plug in the smaller diameter, 1.5? So we can design a pin joint for the gear.
It's about, that's 0.362.
362. So we could use a 3/8 there as well. All right. Could I use a 5/16 here? That might be better. I don't know. 5/16 would be 0.3125. So if I wanted to shear pretty close to the design, then that would be better. Questions, comments? Really not much flexibility with the pin. If you really want the pin to shear at a certain amount, you can buy what's called a shear pin. That's designed to fail at a certain torque, and put that in instead. And then you don't even have to go through this. It's easy. Questions, comments? I see frowns.
Shear pins only work if you have the groove lined up.
Do they? That makes sense. Yeah. So you'd have to design it so that the groove gets into just the right section. Yeah. There must be precision ground down to the diameter or something. All right.